Yeah, today we'll take another example of arrays. We already saw the sorting algorithm earlier when we did analysis of algorithms. We did the selection sort, and we found that the dominant computation was exchanges, and we found that this is an order n squared algorithm. Unless otherwise specified in this course, big O will generally refer to the tightest bound on O that we have. We look at other sorting algorithms today, which are of the order n squared variety. So let me call this A. B will be the bubble sort. It's also called exchange sort, and there are various other names like sinking sort and so on. And a third variety of this algorithm is what is called the insertion sort, which is what we as humans do. All these are order n squared or theta n squared algorithms. So let us look at the bubble sort algorithm. And once again, we will take an example and work on it. Suppose we had this array of 8 elements. And these were the elements that we had. And 39. So what is done in bubble sort is, again, we assume that the array goes from 1 to n. And let us say this is A of 1, A of n. There is a theory by Professor Dijkstra that counting must start from 0, which is perhaps correct, but I'm going to count from 1 because I'm so used to counting from 1. So what is done in bubble sort is that you start with the first element, compare it with the next element. Now you get a new array, and then what you do is you make sure that you compare it and exchange it if necessary. So notice that 30 and 12 are out of order. You compare whether 30 and 12 are in order. They're not in order, you exchange them. So you get 20, 12, 30, 18, 8, 14, 41, 3 and 39. Bear with me, I'm going to just complete this one pass through the entire array so that you get an idea of what's happened. So next, these two elements have been, so I'm making one pass through the array and just reordering elements which are out of order. Now, first element was compared, so 12 and 30 are in order. I compare 30 and 18, and clearly 30 and 18 are again out of order. So I once again exchange them to give me 12, 18, 30, 8, 14, 41, 3 and 39. Okay, we still at A1 here and AN here. So clearly these three numbers, these three pairs of numbers, I should not say these three numbers here. So now we come up till here, and next what am I going to do? I'm going to look at 30 and 8. Again, it's out of order. So let's make this complete pass. Bear with me, I'm just doing this so that you know why it's called bubble sort. 18, 8, 30, 14, 41, 3 and 9. Okay, So let's do the few more passes. And now what's going to happen? 30 and 14 are going to be compared. We have 12, 18, 8, 14, 30, 41, 3 and 9. Okay. So now next we need to compare these two. So we have 12, 18, 8, 14, 41. Oh, sorry, it's in order. So I leave it as it is. I don't do anything to it. It remains as 30, 41, 3 and 9. Then I go on to the next element. These two are out of order. And I once again perform an exchange. Okay. 12, 18, 8, 14, 30, 3, 41, 9. And of course, finally, compare these two. And we have 12, 18, 8, 14, 30, 3, 9 and 40. So what happens is over here, interestingly, now if you look at what has happened in the array, let's start with this. This is where we started. So what do we find? 41 is the largest element. So at the end of one pass through the array, the largest element is bubbled to its correct position, okay, which is the end of the array. Okay, that is what bubble sort is all about. So now once you have, so if you look at it, this portion is actually sorted. Now you repeat the same process on this portion of the array. Start with this element again. These two are in order. 18 and 8 are not in order. So you swap. Then 18 will be here. 18 and 14 won't be in order. Then 30 and this, up to this part will be in order. 30 and 3 is not in order. 30 and 9 are not in order. And I had a 39 somewhere. No? Where did the 39? Oh, this is 39. Sorry. 39. 30 and 39 will be in order. And you get the next pass and so on. So you understand the idea of what we are doing in terms of bubble sort. So we repeat the difference. So what we do is, you may wonder, is it very similar to selection sort? Where in the selection sort, what did we do? We started from the all the most minimum element, what the sorted portion of the array was was at the beginning, whereas in the bubble sort, the sorted portion of the array is at the end. It's a little bit different, and we'll see why it's going to be different. And the reason why it is going to be different is the following, that here bubble sort stops when during a particular pass through the array, there are no exchanges made. No exchanges made. Okay. So let's see what this will be done. And or alternatively, you stop after, if every pass involves an exchange, to stop after n passes through the array. So obviously, if you look at the uh, time complexity, what's it going to be? One pass through the array, you looked at how many elements here, you looked at all, it made n minus 1 comparisons here. And so once again, and for every pass, because we're going to take the unsorted portion, now you will do n minus 2 comparisons and so on. So it comes to be an order n squared algorithm. So let us write the algorithm over here. And let me write this. Maybe I should write this more as a P module. It's more a procedure module. I'm going to change this. It's a procedure module because it's not really returning anything back from the function. P module bubble sort of the array is sorted in place. Okay. So I have a pointer to the array int n. Okay. Now I have variable int I. This, let us say, is an index to for number of passes through the array. And is a variable that I define. Then int j, let's say, is the index for the unsorted portion of the array. And int t, let's say, is a temporary variable that enables swap. Okay. You could also write a separate function for swap if you like. So initially what do you have? We want to sort the array A of 1 to n into ascending, actually you should say rather non-decreasing order by uh, using bubble sort. Okay. Why do you say non-decreasing? Because there can be repeated elements. Okay. And we have one more variable called sorted, which is a Boolean, which will keep track of during each pass through the array, whether there was an exchange or not. Okay. Let's say we have this. So we start, let us assume that assert, or we're not giving n less than 0, at least one element is there in the array. And we start with I being initialized to 0. And let me write this first and then afterwards write the loop invariant. While I less than n, and we will also assign sorted to, while not sorted is true, sorted to false. Okay. While I less than n and not sorted is true, do, oh, I'm setting it here. So every pass we can set this variable sorted. We have to set it in every pass actually. Sorted is assign the value of true. I tell you why I'm doing this. Okay. Notice that we're setting it inside. So before this, uh, we will assume that sorted is false. This perfectly fine. Okay. And then what we'll do is we assign the value of sorted to true, assign I to I plus 1. I'll come back to the loop invariant in a minute. And for j going from 1 to n minus I, do if a of j greater than a of j plus 1, then swap t is assigned the value of a of j is assigned the value of a of j plus 1, and a of j plus 1 is assigned the value of t. Okay. Then notice that we say sorted, we again reset it to false. I'll tell you why we do this. End if, end for, and end while. Okay. So let's see what the post condition will be. We assert that a of 1 to n is sorted in non-decreasing order. Okay. Now let's go back and look at what the, okay, let's see what we're doing. We started out with, sorry, a little bit confusion initially. I started out with sorted equal to false. And then what we're doing is, notice that not sorted is true. That means what? Sorted is false. I assign sorted is true. As soon as I get into the loop, I say it's true. But then when I'm comparing here, and if I make an exchange, because there's an exchange that has happened, I say that means there is an inversion. What is an inversion now? If I less than j, but a in this particular case, if a of I is greater than a of j, then we say there's an inversion over here in terms of the order. And that's what we are checking here. There's an inversion here, and we set sorted equal to false. Okay. Then what do? We go to the next element in the array, again check if there's an inversion, and repeat this. Now suppose what happens is sorted is set to true, and there's no inversion through the array. What does it mean? The array has been sorted, and what happens? And not sorted was true, right? So it'll exit out of the loop. That's the most important part. Okay. So what is interesting is if you compare it with selection sort, in selection sort, we were making an exchange every time we pass through the array. So here, if the inversions are small, then bubble sort can give us a better time complexity. So let us look at what the loop invariant should be here. And what do we have here for the loop invariant? Let me perhaps write it in a different color. Let's see, this is the loop invariant here. We have I less than or at the end of the iteration, okay? Because sometimes these things don't get satisfied before you enter the loop. And we have a of n minus I plus 1 dot 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 n is ordered, and all of a of 1 to n minus I is less than or equal to all of a of n minus I plus 1 dot 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 n. Okay, that's what we mean here. So this is our loop invariant. And once again, going through the array, we initialized I equal to 0, I less than and sorted to false and not sorted here. These, as soon as we get into the loop, we assume that it's going to only go through one pass. That is, there's going to be no inversion. We assume that. And as soon as you find even one inversion, we set sorted to false. So it'll go back to the while loop as long as I is less than n. Okay, let us do the analysis of this algorithm. And the time complexity of bubble sort, time complexity of bubble sort. Let us look at what is the best case and what is the worst case. Okay. And for this analysis, what are the relevant parameters? Number of comparisons as before, and number of exchanges. If the array, let's look at the best case. Best case means what? Array is already sorted. Okay. 0 exchanges. But surely we need to perform n minus 1 comparisons. Okay. Now, what is the worst case? We have an array in descending order, and number of comparisons is equal to the number of exchanges, and this is of the order of n into n minus 1 over 2. Okay, so the time complexity of bubble sort is order of n squared. Bubble sort, in fact, is not preferred even over selection sort, primarily because exchange is a very expensive operation. Okay. So we'll come back, we'll stop here, take a short break, and come back to the next part of the course or the class.